This is a video about doxycycline, a semi-synthetic antibiotic, and today we'll be exploring its history, structure, drug targets, mechanism of action, pharmacodynamics, synthesis, what does it treat, and its side effects. Doxycycline is semi-synthetic, but some tetracyclines are produced naturally by Streptomyces bacteria, such as chlorotetracycline, which was the first one to be discovered. It was isolated from Streptomyces aurifacines obtained from samples of Missouri soil in 1945 and marketed as a medicine in 1948. In 1952, it was found that you could hydrogenate chlorotetracycline under mild conditions using hydrogen with a palladium and carbon catalyst and produce tetracycline itself. Pfizer was the first company to isolate oxytetracycline from Streptomyces ramosus in the soil near their Indiana plant. Charlie Stevens' group at Pfizer worked on further analogues and created one with greater improved stability and pharmacological efficacy, doxycycline. It was clinically developed in the early 1960s and approved by the FDA in 1967. Doxycycline was clinically marketed under the brand name Vibramycin, becoming Pfizer's first once-a-day broad-spectrum antibiotic. Doxycycline has a basic backbone of 4 6-membered rings. It has 10 heteroatoms, 8 oxygens, 5 of which are hydroxyl groups, and 3 are carbonyls. The remaining 2 are nitrogens, an amine and an amide. This means it has 6 hydrogen bond donors and 9 hydrogen bond acceptors. With a molecular weight of 444.4 grams per mole and a log P of minus 0.2, doxycycline fits the Lipinski's rule of 5 pretty well. It works by interfering with bacteria protein synthesis, also called a bacteriostatic drug, and this lipophilic structure helps it do this because it allows the drug to pass through the bacteria's lipid bilayer.
Drug target. In prokaryotic cells, the target for doxycycline is the 30S ribosomal subunit. The 30S subunit is the smaller part of the 70S ribosome and is made up of 19 proteins, a small polypeptide of 26 amino acids, and the 16S RNA chain. The 30S ribosomal subunit has a crucial role in the mRNA translation. Initiation factors IF1, IF2 and IF3 are necessary in order to complex 50S and 30S ribosomal subunits for the initiation part of the translation process to synthesize the protein. I am now going to talk about the structural activity relationship. The main interaction between the contact region of the molecule and the surface of the ribosome is hydrogen bonding. The groups that feature in the contact region are all the groups between and including the dimethylamine on the A ring and the hydroxyl group on the D ring. As a result, removal or substitution of these groups can alter the activity of the molecule. Removal of the dimethylamine group reduces activity. Substitution of the amide by aldehydes or nitrites reduces activity. The stereochemical configurations of the hydroxyl group and the hydrogen at the 5 and 6 positions of the A ring are key to activity. Also, alterations of the ketone and ethanol groups reduce the activity. I'm now going to talk to you about the binding interactions of doxycycline. Doxycycline interacts primarily with the exposed sugar phosphate backbone of H34 or the TET1 binding site. The majority of interactions of the drug are through hydrogen bonding interactions between the oxygen atoms on one side of doxycycline and the phosphate backbone of H34. These interactions are often facilitated by a magnesium ion, which doxycycline is often found to be complexed with. There are also additional hydrophobic interactions between the molecule and bases pointing out of the H34 towards the A site, which help to hold the molecule in place. Doxycycline primarily binds to the H34 as a complex with a magnesium ion or a calcium ion, as this is the way that it commonly exists in biological solutions. Mechanism of action. Doxycycline reversibly binds to the A site of the 30S ribosome subunit of the ribosomal mRNA complex. It competes with the aminoacyl RNA for the A site, preventing translation of the mRNA into a polypeptide. On a larger scale, this prevents the synthesis of bacterial proteins, preventing cell growth and proliferation. This also highlights why tetracyclines are bacteriostatic and not bactericidal, as the tetracycline prevents the bacteria from reproducing rather than killing them.
Now on to the pharmacodynamics. Doxycycline has the highest protein binding and the best half-life of all the tetracyclines, with 19% bound in the plasma and a half-life of 18 hours. It also has a very high oral availability. 90 to 100% of the oral dose was found to be reabsorbed in the GI tract in a study of fasting adults taking doxycycline. However, like the majority of tetracyclines, it's actually not metabolized at all. After administration, it gets concentrated in the liver, then excreted by bile into the intestine for reabsorption. It's then cleared renally and fecally, and without hepatic metabolism, it avoids the first pass effect, which means it is excreted unchanged. Although it can be deactivated in the intestine by chelate formation with cations such as calcium, magnesium, and iron. Therefore, administration with other medicines such as antacids can reduce absorption along with food and milk. The starting point for the synthesis was the enantiomerically pure ester, structure 2, prepared by the fermentation of benzoic acid, structure 1, to the 1,2-dihydrodiol, followed by the epoxidation, rearrangement, and silylation. Acylation of structure 3 with 2 gave the ketone structure 4, when on exposure to lithium trifluoromethane sulfonate, underwent a diastereoselective carbon-carbon bond-forming reaction. After selective desylation with TFA, it produced the alcohol structure 5. The authors speculate that this reaction is preceded by initial SN2 epoxide opening by nitrogen, followed by ylide formation and a 2,3 rearrangement. Since doxycycline is a broad-spectrum antibiotic, it is used to treat a wide range of bacterial infections, as well as having some efficiency in treating against protozoa. One use is for the treatment of urinary tract infections. This kind of infection occurs from bacteria such as E. coli entering the urinary tract. If left untreated, this can progress to cystitis. Another use of doxycycline is in the treatment of acne. Acne is believed to be caused by a number of factors, including genetics and hormones. However, an overgrowth of Propionibacterium bacterium is also considered a factor. Gum disease is also treated by doxycycline, since it is caused by a layer of bacteria coating the gums and teeth. The bacteria that cause this infection is displayed in the slide. If it is not treated, it can result in the loss of teeth, bad breath, and bleeding gum. Lyme disease is another bacterial infection caused by Borrelia burgdorferi, which is treated with this drug. Some sexually transmitted diseases can be treated by doxycycline, such as chlamydia, Mycoplasma genitalium, and Ureaplasma ureolyticum. Chlamydia is caused by Chlamydia trachomatis, and the latter two are caused by Mycoplasma bacteria. For these three infections, symptoms are often similar and include urethritis, painful urination, and proctitis. Bacterial pneumonia is caused by bacteria such as H. influenza, C. pneumonia, and C. burnettii is also treated by doxycycline administration. Pneumonia is commonly an infection of the upper respiratory tract. However, it can spread elsewhere in the body to cause sepsis. This can lead to fever, confusion, and chest pains. Interestingly, doxycycline is also used in the prevention of malaria. However, only if the virus responsible for the infection is Plasmodium falciparum. It is given before a person goes to an area where malaria is present, and therefore is not used to treat malaria, but to prevent it. It does this by impairing the apicoplast genes of malaria so that they proliferate abnormally. Vomiting, nausea, and diarrhea are all severe side effects of doxycycline. This occurs due to the elimination of flora in the gut, and in some cases, this leads to anorexia. After long-term use, weight gain can be a side effect because the bacteria that helps digest fats is also eliminated by this drug. Finally, in some cases, doxycycline induces photosensitivity in skin, which can lead to flushing. To summarize, doxycycline is a relatively broad antibiotic. It has been around since 1967 when it was approved by the FDA, and since then has been used to treat a wide number of conditions. We hope you enjoyed watching and learned something interesting from this video.